Good morning. So we finished yesterday with this calculation. Now we continue with the calculations of the other two sheets, but before we do that, maybe you have questions. All is clear. Nobody has questions. Okay. Then what we will do, we will now go first to this very simple case. We will try to calculate precision, but here I will do a few more things, yeah, not just. And then we will look at the slide number 3, yeah, which is the most demanding or most potentially difficult. So obviously we here can simply calculate standard deviation, yeah, because it is always the same something. I guess you probably got something similar. Yeah. But now this precision, we can call it precision, obviously, yeah, but there's one more way to say what is it besides just precision. And I'm now speaking about mathematical presentation, not the meaning in terms of analytical chemistry. It's very, of course, very vague question again. But no, that's not the my turn.
It is the within lab reproducibility.
Okay, yes, this is the meaning. I did not mean that at this point with my question, but okay, let us already mark this. Can you explain why is it within lab reproducibility?
Because it's the same control sample analyzed during different days. So it takes into account different effects that could be happening during that long period of time.
Any opinions about the time period, about the length of the time period? Short. So we cannot call it long-term within lab reproducibility. Call it. All right. But now, yeah, what I meant here actually, and I recognize it was the question is so vague that it's really impossible to answer reasonably. This could be called absolute precision. Can anybody say now what does it mean, absolute precision? Absolutely correct or something else? Take the microphone.
So meaning is that it is not compared to any other quantity?
Not really.
Absolute means it is the same unit as with the...
Exactly. Presented in the same units as the measurand. We did not really discuss absolute precision, but we did discuss absolute and relative uncertainty. So actually, you've already heard those terms here. Okay. Now, let us also try to calculate relative precision. Later on, we will be also needing that one. What should we do to calculate relative precision out of these data? First, need the mean. Otherwise, we cannot. There's a function called average for that in Excel, which again, I don't know exactly how it is in your language, but I think you probably know this. You have used Excel. And how now we call, or how can we now calculate relative precision? Have absolute precision and mean. How do we calculate relative precision? Yeah, exactly. We divide the standard deviation. No? I have put here two more. Ways of presenting, and very often people don't present just as ratio the way I did here, although it's perfectly correct. There's nothing wrong with it, but they present as percent. And here I have formatted this cell as percentage. So this is like the Excel way of showing the percent. And then it is also possible to present it like this, that you literally take this value and multiply 100. Now write percent here. All these present relative precision, and they will be useful for us later on, because sometimes we do uncertainty calculations or other calculations, not with absolute, but with relative quantities. Now, it is these three ways of presenting are distinctly different or the first two and the third one are different in one respect. In this case, the value of cell F7 is 0.08. In this case, the value of cell F8 is also 0.08. The fact that it is pictured 8.0 and percent is the way how Excel shows it, but not what it is. It still is 0.08 in the cell. Very easy to check that, Let's try. Do this thing, let's say, plus something, for example. +1. Okay, and now it also formats as we can do it in. Let me format this cell as a number. Okay. Now, if I add to this just 1, I get 1.08. And how you can recognize is that you see the percent sign is inside the cell, not outside. Very important. And finally, here in cell F9, the value of that cell is 8, not 0.08. And percent is outside. You may ask that, or let's put it this way, that neither of these two is wrong. Both are fine. And people use both of them. Some people use more one and some more the other, and then it's so on. But I would recommend this way of using, not multiplying by 100%, but rather formatting cells accordingly. I will explain later on why that is useful. That makes certain calculations less clumsy, because if you start multiplying by 100, then if calculation becomes slightly more complex, you will always have to, okay, I need to divide by, no, I need to divide 2 times by 1. No, now I have to multiply by 100. So this 100 is floating or sitting on your head all the time. If you don't multiply by 100, you can do like all the percent calculations without ever thinking that there is something like 1. We will come to examples when we do calculations, then I will explain what it is. But I don't consider neither way wrong. So if on exam you use this, it's perfectly fine. It's up to you how you manage your calculation. I will show you. I think this cell was actually pre-formatted already in the file, but if it's not, or let's go here, for example. We can also format this cell as percent. We take here, there are all kinds of formats, and we click percentage. And in fact, in my Excel, it even offers percentage as one option, like separately here. So when I click now here, it also becomes percent immediately. So it's a useful thing, actually. Okay. And now, perhaps we also calculate the number of degrees of freedom, just for rehearsing. Number of degrees of freedom very often denoted as df. And now, of course, we can just calculate how many cells we have, but we can also do like this. Count function counts all cells which have numbers in them. And count is good in the sense that if you have blank cells in the range, it automatically excludes blank cells. So it only counts those that really contain numbers. If there are cells that contain text, then those are also excluded. Yeah. So it only counts cells that contain numbers. Sometimes it's pretty useful if it knows how to reject textual and. So, any questions here? These are quite simple things. Yeah, Caleb.
So I noticed that the data starts drifting upwards a bit for every fourth experiment for about 1 gram per 100 grams. Was this done on purpose, or are those things like even worth mentioning or noticing?
It is very much worth mentioning. Yeah. And indeed, there is some upward trend here. And I would perhaps not go deeply into this at the moment, but when we go to the quality section or control routine quality assurance or control chart part of this course, then we will examine drifts in data in more detail. Otherwise, yes, these drifts often tell something. Yeah? Your sample is contaminating or something. Okay, if you determine fat content and fat content is 20 grams per 100 grams, the contamination certainly is not an issue. It's probably something with the measurement method. Okay, if no questions here, and we now go to this one. Who tried to calculate this? Who managed to get something calculated? Aha, okay. So let's see. How do you do then? You calculate standard deviation from these values and then standard deviation from these and so on, or you do something different? No? Interesting. How do you do?
I first of all sorted them by the number of the sample. So I'm not sure if you wanted to explain this or not, but there is a filter button. I used this to do it automatically, and then I used the sample numbers to calculate full standard deviation as in the previous example, because if you analyze them by date, then there is not much of a use in that data.
Very correct. Indeed. If you just calculate standard deviation from these values, what will be the meaning of that standard deviation? It will essentially tell us what is the variability of analyte between your different samples. Which is not very useful. It might be useful for some application, but it certainly does not tell you much or does not tell you anything about your method. But the reason why we are calculating these things here is that we want to characterize our method and use those data later on in some calculation. Yes, I did not plan to show the filter thing, but actually it's a good idea. Yeah, let's do it. Yeah. So indeed, if you take the data section of Excel, then you find here something that is called filter. And when you click on it, yeah. Okay, I clicked too fast. When you just click on it, then you will get these small things here, yeah, like small arrows. Try and see if you manage. Works. And now you can sort these data according to different things. And right now it is useful to sort according to sample number, yes, smallest to largest. How it is. Now, of course, those lines that are here do not necessarily mean anything. The lines were meant to separate the different days, but now those lines don't. They accidentally overlap now here on the bottom, but here they don't overlap. Yeah, so that sample 2 is here. And now, indeed, you can calculate standard deviations from the adjacent values like 2 and then 4 and so on and so on. Did you manage? Should I show again? No, it wasn't. No, it wasn't sorted. So this is how it looked in the beginning. Okay, let me ask like this. Please raise your hand who managed to sort. Most of you. Please raise your hand who did not. Haider, how is it with you? I see you're still doing, or you managed? All right. Okay, then let me also then sort my own thing here again. Yeah. And now we can again do pretty much the same calculation. N-1. Yes. Let's put again. All right. And we now can do in pretty much the same way. And Hans, do you want to teach me now how to do this automatic thing? So you mentioned yesterday after the lecture that you know how to do it in such a way that the standard deviations here will be immediately like assigned to these samples. There was one student in the past who also knew how to do, and that student showed me, but I've forgotten and I've lost that file. So I. And there's comma, not semicolon. My Excel, magic, yeah, okay, yeah, it should be. Yes, I understand. Yeah. You want dollars? Yeah, yeah. Yeah, it got a little bit carried away. Yeah. Okay, let me try to. Interesting. If it doesn't work, then I don't understand why it works.
Have the order right.
Yeah, but this would raise the question why the first calculation is okay.
I got the value, and value doesn't make a lot of sense. 10.2 and 11.2, and it calculates the standard deviation.
Yes, I see now. Yes, this is wrong. Yeah. The standard deviation itself is also wrong, but if I remember correctly, if was supposed to be inside standard. I try to recall what the other student, by the way, was also from the Philippines. So it appears that there's very high level of Excel knowledge in that archipelago. Yeah. We cannot perhaps stay too long on this, but let's spend a little more time. Maybe Hans will work out how, because it's actually a very useful thing. Practice. But Hans, in your PC, it works fine. And you inserted the formula the same way. Yes, please do that. Yeah. Okay, sorry, but let's take a little more time. Yeah? Interesting to look at it. Try comma, but comma is typically, yeah, you see, it doesn't really take comma. Ah, yeah, you don't see the error message, yeah, in your screen. Has to be semicolon. Of course. Sorry. Of course, there can be some Excel version issue, but I don't think that can be a big, because usually there is, since people use different versions of Excel, then if it works in one, it should work also in others. Otherwise, it would be a big mess, yeah, if people share files and they don't work. But I will, when I get file from Hans, let's see to what it converts it in my Excel. Oh, by the way, while we are waiting for the email, let me ask you something. I haven't yet touched upon dollar signs here at all. Yeah? Please raise your hand who understands what dollar signs do in formulas. Apparently everybody. Please raise your hand who does not know what dollar signs do. Oh, please raise your hand who feels uncomfortable with dollars. Okay, everybody knows. Very good. Yeah. So dollar signs fix numbers or fix letters, while usually when copying, letters and numbers can change. So no email yet.
I got the formula working in my.
But if you now look at what the formula looks here, can you see the difference? What could be wrong here?
Oh.
Yeah, you see, in our national like Excel, yeah, it is the thing that in most people's Excel is comma is semicolon in our case. Because many Estonians put, instead of the dot, they put comma as decimal separation. Yeah? Right? Here it is. All right. Very interesting. Opening now your file. Ah, I know what. I got it. Oh. This is one very subtle difference between my Excel is slightly older than yours probably. So it's a very subtle difference. The formula is essentially the same, but it is entered in a different way. Let me see. Yeah? And if you look here, you don't see any difference at all. But look now very carefully here. And you see that formula has around it those wavy brackets. In your case, when you insert such things, I think you simply press enter. In my case, I need to press Ctrl Shift. then it makes it the same way. We will later on come to some other functions that have those wavy brackets. Those wavy bracket functions are actually array functions. So this is what makes them different, yeah. And as soon as I saw the file from Hans, he already had those wavy brackets. And the trick is that in earlier Excel, if you wanted to get those wavy brackets, you had to press Ctrl-Shift-Enter. In modern Excels, you can press simply Enter. But later on, when we will look at the linest function, then it might happen. I'm not so sure, but at least in the past, there were sometimes situations where there were also drawbacks with this, that it's directly automatically doing that. But let's leave that discussion aside. In any case, we managed now. Please raise your hand who managed to do the same thing. How long, Haider? You cannot. Thank you, Hans. So I will leave in one sheet the old way, how I so that's it, and the other sheet I will put this. And of course, this approach, this approach has the additional beauty that you don't need to do the sorting. Actually, let me revert the sorting. Then it will be like even more instructive. I will remove this filter. And I will copy the same data. So now there's no sorting, and you see the numbers are still exactly the same. Yeah. Let me check. Don't want any All right, yeah. Sorry for the small intervention. Yeah. And now we can also try to calculate this n minus ones using a function. Yeah, this can also be done using a function because if data are not sorted, not so easy to count. Moreover, if you don't have 5 samples, but 55 different samples, imagine this long list of validation data, 55. You don't want to do this by hand. Yeah, you want to have some function. So let's try. We can now try to count like conditionally. So there's another if kind of function, which this time is called count if. Count if. And now comes the range. And now comes what is it that you are counting? And you are counting the numbers that are, and you are counting the numbers that are in column E, so E6 in this case. Oh. So let me go, and here also we need to put the dollar signs like this, so that the array would also always be the same. So I keep this function, and -1. I keep this function visible to you. So this should now give the number of degrees of freedom for every one of these standard deviations by counting how many times this specific sample appears here, and subtracting 1, because for n-1, we have to subtract. Try to insert it. This one is not an array function, so here you should not have any of this problem that we encountered here with the standard deviation. That count if we could have used also in the previous sheet. Yeah, perhaps next year I will advance this whole teaching and start using those functions more. Let me do the copying. Let's see if it actually works correctly. So 4 times. Yeah, I think it's correct. I saved, so you can now get my file if it doesn't work. Who managed to do this count if thing? People on the internet? Ekta, Elvin, Golam. I hope you managed to keep pace. Yeah. Okay, now S squared is trivial. Yeah. And now, those of us who are lazy, don't want to work very intensively, can simply take and copy these lines or these cells from this previous sheet and paste them exactly into the same location. Then it will be calculated exactly the same way, because calculation of the pool standard deviation from these squared values and these n-1s is the same. Yeah, there's nothing different. So if I take this, I need to remember that I should now paste it to E13 because it has to be positioned the same way with respect to these things. So I put it. Paste. Perhaps I will put a few more decimals here so that you will see whether you have the same. The file is saved, so whoever wishes to see those formulas, yeah, you can. And now again, meaning of this precision. What is it? What kind of precision is it? Yep.
I would guess that it shows us within lab reproducibility, again during short time period.
Any other opinions? No. I also don't have other opinion. It is within lab reproducibility. And again, what matters is that every sample, like let's take sample 3, was measured on 10th of February, 13th of February, and then on 18th of February, every sample was measured on a different date, meaning every standard deviation is between days. If you take between day standard deviations and pull together, you still get between day standard deviation, which is within lab reproducibility. However, the time period here is very short. If we run the experiment like this, then we actually don't even need to look at when is the first and when is the last. We should look at the time frame or time period for the same sample. So if the overall exercise even takes a year or two, but every individual sample is only measured during a time frame or something like week or two, then it still will be a very short term within lab reproducibility, because all those standard deviations that you are pooling still convey changes only across a very short time. So it is within lab reproducibility or intermediate precision, but the time frame very short. So the time frame is so short that you cannot really, you should not use this precision in situations when you really need within lab reproducibility. Like, for example, in Nordtest uncertainty estimation, I would say this is not okay. It's too short.
So
Yes,
if
Heidi.
I understand it correctly, what you mean is that let's suppose all the samples take 1 year to be measured. So for the individual sample, the time frame will be short. Is that what you mean?
Yes, for example, it would be much better if this sample 1, okay, it was measured only 2 times, but that's not an issue. But it would rather be better if it would not be measured here 3 days later. But if sample 1 instead would be measured, let's say 02/03/2009. And here we perhaps suppose we did not measure sample 1 here at all, but instead we measured it on this day. Now these two measurements of sample 1 are apart by roughly 1 year, so that now their difference really conveys information with all different things that have changed mean. Of course, this requires that sample can be kept intact for 1 year. Can be sometimes difficult. But with freezing possibilities, most materials actually can be kept. The large majority of analytical chemistry samples can be successfully stored for many months in the most common freezer like the one you have at your home. So -20 or -18 or whatever it is suitable for the large majority of things. And then there are those very delicate bio things which really do not preserve at -20, but those almost, I think, without exception, can be preserved at -70. Of course, -70 freezers are not available in every analytical lab, but they are available in bioanalytical facilities usually. And then you still can store for a long time. And in principle, you can build up measuring your within lab reproducibility just with duplicates. So suppose all your samples are very small, you only can do 2 measurements. Then what you can do is that every sample you measure now and 9 months from now, or 8 months, or 12 months, or 7 months, or 13 months, etc. Yeah? So every sample you split in 2 now and then in the distant future. The next sample again now and in distant. And then when you then calculate this kind of pooled standard deviation, you will have very nice, good within lab reproducibility estimate, although you did not have a large amount of control samples that you can keep for a long time. Okay. So I'm again saving the file. Now it should be available for you on Moodle and in this form as you see it now. Perhaps I still do this also for education purposes, so that it now will contain. Yeah, now all the numbers of decimals in the results are pretty okay. So now it's fine. And let me save. And here I would now finish this calculation example and go back to slides unless you have questions. Yes. In this case, what matters is time difference between individual samples, not the overall time difference. Sorry, I said wrongly. What matters is time difference between replicate measurements of an individual sample. Yeah, this is the correct way to say it in English. Okay, then I take back control here. Perhaps we can now to save this lamp and everything. Yeah, there's no need to have 2 beamers running simultaneously. And now for these slides, I still have just one last slide, which actually we already discussed last time briefly, but let me come back here for a moment. Yeah. So what is meant here now? This now refers to this repeatability thing. and refers to our first calculation, so that if you calculate repeatabilities on different days and pool them, what you get is still repeatability, yeah, even though the experiment took place on a different day. And also, as I already said, let me just repeat, what you put into pooled standard deviation is what you get out. Yeah. You pool repeatabilities, then the outcome is repeatability. You pool within lab reproducibilities, the outcome is within lab reproducibility. And now comes an interesting question. There are two options. What is better if you evaluate repeatability or if you evaluate within lab reproducibility? Is it better that you do it as it usually is done, that you have just the same sample, yeah, and you do a number of replicates with that same sample, yeah, with that same sample, or you do pooled standard deviation. You do pooled standard deviation using different samples. Paint this red. Which of these gives you a better characteristic of your method? What are your opinions? Why so? Not really. You do not calculate the standard deviations between different samples. You only calculate like within one sample. Yeah, Maitane, can you take microphone also?
I would say the other option, the pooled standard deviation with different samples, because it will give us an idea about the general condition of our lab, like what is happening or what will be the principal sources of variability, instead of like just doing a lot of measurements for or replicates for just one sample.
I would say if you do with just one sample, you also get information if something changes in lab, because all the time values are like this, but now suddenly they are like higher. This tells you something that something is going on. Any other opinions? Yeah, go ahead.
Maybe it depends on the objective you have, because you want to assess the repeatability, so you should use the data series with your same sample. You want to assess the within lab reproducibility, it will be better if you take pooled standard deviation, different samples within time.
Yeah, okay. Both for repeatability and within lab reproducibility, all the standard deviations always have to be with the same sample, yeah, not between samples, because then you will be simply quantifying differences between samples. I would say there is no such distinction here. I would say that for repeatability and within lab reproducibility, there is no big difference between, like, there's no big difference for which of these two you are trying to answer this question. Okay, let me try to. This is a typical question that often happens where there is no right or wrong. Sorry, Gleb, you wanted to say something also. I forgot. Yeah.
My answer is it depends. What is your task in the lab? If you usually analyze same kind of sample with little to no variability, then obviously repeatability gives you more information, more usable information, or maybe give you the same amount, to say at least. If you pull a lot of standard deviations from different samples, then it tells you how your method behaves with different samples of different concentrations. It gives you more information, a wider approach to estimate how good your method is in different kinds of situations.
Okay. Yeah, you said well. Okay. This is a question where there's no clear right or wrong answer. It's very much opinion based, and it can be done both ways. In any case, it's very useful to evaluate repeatability and within lab reproducibility, whichever way you do it. But now there is one distinct difference, and Gleb actually pointed towards it. If your samples are really very uniform, which often happens in the industrial production, where the uniformity of production is like the key thing. You want that all your products day in, day out are all the same. Then there's not much difference, and then there's also no real need to work with different samples, and it is certainly simpler to just have one control sample, especially if we think about within lab reproducibility. But now if you are some food control laboratory and then there are different foodstuffs brought to you for the same contaminant, maybe your method is validated for those different foodstuffs. Then if you pool standard deviations with samples of different level of complexity, then both repeatability and within lab reproducibility will be average repeatability or average within lab reproducibility across the different, let's say, complexity levels of samples. In that case, in principle, it is better to run those things separately for different samples. But it can sometimes happen that you don't get large numbers of those different samples, and you don't have statistically representative lots to run them separately. In that case, that pooled standard deviation thing gives averaged repeatability and averaged within lab reproducibility across different samples, while having just the same control sample gives you just the within lab repeatability of this same sample. And if the samples from your customers happen to be different from this one, then that within lab reproducibility does not necessarily reflect the level of complexity of the customer sample. So that it's a way of getting some kind of, let's say, averaged values of either repeatability or within lab reproducibility over different samples. Yes, this red case. But having just one sample makes everything much simpler. So it's simply much simpler to organize your work, which also has a merit. So we stop here with this part 2, unless you have questions. Apparently not. And we now go to part 3. How are they different, you mean? Interesting. Yeah, they are not really the same thing at all. Either. Did you get an answer from Gleb?
I will explain to him.
Okay, let's do so. Yeah. Many thanks, Gleb, because indeed, yeah, I agree that would perhaps not be a good idea to now rerun the lecture on explaining the difference. I tried to do that pretty comprehensively. And either if eventually you still don't understand, you can come to me. All right, but now let's now go to real measurements, and also specifically now we start looking at this so-called ISO-GAM modeling approach for measurement uncertainty evaluation. First of all, again, some definitions and concepts. We can speak of measurement, either direct measurement or indirect measurement. So direct measurement means that the measurement instrument shows you some value, and this is the measured value. Like if you look at the clock, this is time measurement. So you don't need to do any calculations with the time. Or you look at thermometer at your home, or simple weighing. But most analytical chemistry measurements are of the indirect type. And in indirect measurement, the measurand, which oftentimes can be called output quantity. So the measured quantity that you eventually want to measure is your output quantity. You get it by calculations from a number of input quantities. Typical example is if you do instrumental analysis, then the input quantities are all kinds of masses that you weigh. Then you make some solutions, then these concentrations of solutions matter. Volumetric, where like dilutions, etc. Then there are all kinds of peak areas, both for calibrants and for your actual samples. Then there can be some special quantities added for recovery correction or for correcting for some incomplete selectivity, etc. So all kinds of numbers are put into some kind of formula, and your result is calculated. And we can say that most of our measurements in chemistry are indirect measurements. Direct measurements are such that, okay, if you measure pH, maybe salinity, for which there are meters that you just put in and you measure. Also, the salt oxygen concentration measurement can be called direct, although I will later on explain that it is much more complex than might be. So that in all cases when we do indirect measurement, we have some kind of a measurement equation or measurement model, where your output quantity is dependent on input quantities, and F is any mathematical function. And this is explained here. So there are many terms that you can use: mathematical model or model equation or whatever. And if we look at something as simple as titration, then the measurement model can look like this. Titrant concentration, titrant volume, and the volume of your sample solution gives the analyte concentration in the sample solution. If titration goes in 1-to-1 mole ratio, otherwise there will be some 2 or 3 somewhere also in the very. And now I've already explained what combined standard uncertainty is, but now I can give it another, explain it once again. So the typical situation when you get combined standard uncertainty is that you estimate the standard uncertainty of your output quantity by taking into account standard uncertainties of all the input quantities. And when you do that, then what you get is the combined standard uncertainty of the output. So that if you calculate the standard uncertainty of this Cx by taking all these uncertainties here into account, then that will be a combined standard uncertainty. Now, before I continue, maybe anybody wants to ask anything?
the value of a measurement, would it be considered a direct or indirect?
Depends on context. If in, let's say, the thermometer in your home does not actually measure temperature as such, it actually measures conductivity. And then there's a microchip inside which recalculates this and then presents to you. So that small thermometer, if it's a digital one, it has some measurement model inside. But as long as you don't do any like in-depth investigations with it, you can count it as a direct measure. In the case of dissolved oxygen, I'll come later on to some examples. I will show you some things that you actually, that not all of you, but the large majority of you who were at winter school, you have already seen. And I will explain how all that fits in, so that even dissolved oxygen meter actually has some input quantities because it also measures temperature, etc. So it can also be considered indirect measurement. But of course, though that dissolved oxygen measurement that IRIA did, which will be my main example, that reference value, you may remember, those of you who were at winter school, there was some titration that she performed. That is very much an indirect measurement. I'll come to that. Now, the models can look in different ways. First, a very simple kind of a model looks like this. And this is the typical model that you use in all those cases when you measure something which has different uncertainty contributions. For example, you do pipetting and then you remember there's the uncertainty contribution. Pipette calibration, repeatability, temperature effect. So all these would then be like part of this. Yes, you sort of add all those things together. The same about weighing. Clear?
Yes. Does a minus between x1 and x2 has to be a plus, or?
No, it has to be a minus.
You said you add. So
this this arrow specifically points the attention to the minus. Yeah, and so minus has to be minus. You see, if you do just pipetting or something like that, then there is usually just pluses. But in some cases, it can be also minus. But why I'm putting the arrow there is that if you now calculate the combined standard uncertainty of that, then even though here you have minus, here you have plus. When calculating combined standard uncertainty, in rare cases under this square root, you can see some minuses, but these are rare cases. Most of the time, there are only pluses there. And of course, all the uncertainties, as I've already mentioned, have to be standard uncertainties. And also, all these uncertainties are absolute uncertainties, meaning expressed in the same unit. Yeah, so if it's pipetting, they're all in milliliters. Absolute uncertainty. Yeah? All right. Now, the next typical model is that contains only multiplications and divisions. I did not mention here. So this model means that it only pluses and minuses. There are no multiplications or exponents or logarithms or anything. Yeah? Here now we have a model which only contains multiplications and divisions. And if we go back, we see that, for example, this simple titration model exactly obeys this. Yeah? It is only pluses and, multiplications and divisions. And here now again, even though some is here in numerator, some things are in denominator, but you don't put minuses here. You still put only pluses. Now it's interesting. In this case, it was okay, y is equal to this, and UCY is equal to this, and this all absolute uncertainty. In this case, everything here is what? What uncertainties are here? Relative, yes. You combine all relative uncertainties, and what you get out is also relative uncertainty. So we can here. Oh. So as you see, relative uncertainties are useful in many situations. And of course, you can easily get the absolute uncertainty of your output quantity by simply taking this y to the other side of the equation sign here, the way it has been done. I guess you have already heard this. I think this probably is not new. This is why I'm also going like pretty fast. But if you have issues or questions, you of course shout, and then we will look at it in more detail. Now, we take a general case. If the model is not restricted by mathematical operations, but it can be pluses and minuses, multiplications, divisions, everything intermixed. It can also have logarithms and exponents and essentially anything. So for this general kind of a model, we have this general kind of uncertainty calculation. And although this might look terrible, there are some partial derivatives here and so on, I will teach you later on, it's not really terrible at all. It is not actually difficult to use this model in your calculus. And you don't need to be a guru in partial derivative calculation. It can be done much simpler. Now, what is what here? First of all, these terms here are uncertainty components. So these are called uncertainty components. We will use that term frequently later on. Although I did not mention here, but let me also say that these things here can also in this context be called uncertainty components. Uncertainty components. And now uncertainty components are composed of two parts. One is the standard uncertainty of the respective input quantity, and the other one is the partial derivative of the output quantity with respect to that specific input quantity. Those partial derivatives are also called sensitivity coefficients. And this is because they will express how strongly this input quantity influences the output quantity. Depending on how the mathematical model looks, some input quantities might be much higher by their sensitivity coefficients than others. So some are more influential, some might be less influential. But the overall value of every component, of course, depends both on sensitivity coefficient and on the uncertainty of the quantity. So even if sensitivity coefficient is big and the uncertainty small, then the influence is still small. So very useful to know. Now, let me come back here again. There's something that, don't laugh, but I want to still make this clear. When you do these calculations, what are the units of these U's here? What are the units of these U's measurement? Same as measurand, correct. What are the units of these components here? Unitless, yes. So relative, yeah, and this is also relative. So units must always match, yeah. Okay, good. What are the units of these uncertainties? Same as what? As measurand? Let's see, is it really? Let us go back here. These units here might be millimoles per milliliter, but these units might be milliliter. They are not the same. Measurand has units millimoles per milliliter, but this one has milliliters. Oh, let me come back here. Yeah, so, what are the units of these uncertainties? Same as the input. Okay, good, yeah. Of course, I probably don't need to ask, the units here are, of course, units of the measurand. And now comes the last question, now where I'm actually aiming. What are the units of the sensitivity coefficients? Now interesting. Yeah, Haider. For the output quantity you wanted to say. Yeah. Indeed, sensitivity coefficients have units which are ratios of the unit of the output quantity and the unit of the input. This is what is sensitivity coefficient unit. Units are very important. People do terrible mistakes in uncertainty calculus by mixing up and messing up units, and then they get that, let's say the measured value is 10 milligrams per kilogram, but the uncertainty is 10,000 milligrams per kilogram. So, and then they scratch their head, why is the uncertainty 1,000 because of the measurement? And this can very easily happen if you don't pay attention. So units, very important. Yeah. Let me stop for a moment. Maybe you have questions. Then, somewhat prematurely, I will also give you one more thing here, or define one more thing, which is useful to define here, although we will be using it later. This is called uncertainty index. Uncertainty index is found in such a way, yeah, that you can, or first of all, you can calculate for every component separately. So for example, if this is the uncertainty index of the component 2, then it's number 2 that has to be here instead of I. And you calculate it in such a way that you put the square of that component in numerator and the sum of squares of all components in the denominator. And index essentially tells you what share of uncertainty of the output quantity comes from the respective input quantity. Later on, when we will do calculations, we will calculate those indices. I will demonstrate to you why they are very useful tools in learning about your method and understanding where the possible improvements can come from. So that they express uncertainty contribution as a fraction, yeah, of the specific input quantity. And let me ask like this: what is the sum of all indices of the same measurement equation? 1, yes. And very often indices are expressed in percent again, so that they will be like sum up to 100. And we will use them later on. I will show you how to calculate and so on and so on. Now, what I showed on previous slide was a simplified equation. I've been scratching my head over the years whether to do the simplification or not, but then I've always finally opted for simplified equation. In metrology materials, you will find this kind of equation with an additional term, which is much more complex than this term, which stands for correlation. So that our equation, or the equations on the previous slides, is correct for non-correlating input quantities. And in this course, we always make this simplified assumption. If you ask, what does that mean? What does it mean, non-correlating question, or not correlating input? Let me say that, for example, if you have some concentration of some solution, then the volume of something, yeah, and then the signal from the GC, and then like recovery, then these are certainly non-correlated. So that most of the time, correlation is not really an issue. Correlation becomes an issue in some special cases. For example, concentrations of standard solutions made from the same stock solution are to some extent correlated. Because the stock solution is slightly lower or slightly higher, yeah, than the nominal value, it makes all your standard solutions slightly lower. This is what correlation means. That some effect affects all of them the same way. Yeah? Also, for example, volumetric measurements done on this bench are a little bit correlated because of temperature. Yeah? Because suppose I have temperature here 21 degrees centigrade, but all the volumetric were calibrated 20. So all those volumetric measurements that I'm doing here is slightly correlated, but the correlation usually is very small. So that except in some very special cases, for omitting or disregarding correlation typically is not really. One such case is explained in the online course. So whoever is interested in the online uncertainty course, the specific, I think it's section 9 probably, it's the ISOGAM section there, where it also gives some numerical like example how much correlation matters. And what is also good about that, disregarding correlation in that case leads to slightly overestimated uncertainty, which is okay. Would it be strongly underestimated? Then we should not take that. So that let's just bear in mind, we don't look at correlation. It oftentimes exists, but mostly is a very minor effect. So that neglecting it is not really a big. Now, presenting the result I have already discussed, and I think unless somebody now wants to ask specifically about this slide actually has been already on the course. Unless you want to ask something, I would not really explain it at all. When we do the calculations, we will revisit this presentation of the result. Okay, good. And now, this slide also was already absolute and relative uncertainty. And I think here also, at the moment, I don't have anything to add, unless anybody wants to ask anything. This thing becomes really important in Nordtest method. Then you have to think about absolute and relative uncertainty. And now, let's see, we have 4 minutes. Okay, yeah. Let me still say something. So, we already spoke about distribution functions. We looked at 4 distribution functions, and I think I said that most of the time we assume that our measurement results are either normally distributed or that distribution might be some convolution of normal and T or student distribution, yeah, which makes like heavier tails. Yeah? And then K2 is not 95% coverage probability and so on. I think I've explained more or less those. Now, there are several ways how to handle this distribution issue. And on this slide is presented, it's pretty old, but still holds, is presented a very simple, I would say a simplistic approach from the European Accreditation Agency. So this EA is the European Accreditation Organization. And they say the following. If both of these are true, then you can assume that the result is normally distributed. So number one, the model does not contain significant non-linearities. This is now another interesting thing, which not really very well understood. I would say you can assume, or let me come back a moment. So, this model is a nonlinear function, if we look at it. So the output quantity depends linearly on titrant concentration and titrant volume, but the Vx, the solution volume, it's like reciprocal function, which is not linear function. Yeah, it has the shape of this kind. Yeah, or I should show this kind. Yeah, for you. Now, if the uncertainty of Vx is small enough so that within the small uncertainty range, the relationship between these two quantities can still be approximated by linear function, then we can say model does not contain significant nonlinearity. Meaning, it is a nonlinear model, but in terms of uncertainty estimation, we then can say that does not contain significant nonlinearity. However, suppose the uncertainty of Vx is 15% relative. So that Vx is like 10 milliliters and the uncertainty is 1.5 milliliters. It does not, almost never happens, yeah, but just suppose. Then it is a significant nonlinearity. So that you can, the take-home message here is, except in some very infrequent situations, you can simply look at this. If your model in denominator, not numerator, but denominator, has a quantity which has high relative uncertainty, then that is a significant nonlinear. In all other cases, you can say, not really, no significant nonlinear. Okay. Most of the time, this number one holds. Yeah? And now the number two. Number two is like composed of two things. If one of these two is true, then it's fine. Yeah? The first is there is one main source of uncertainty that has normal distribution and has 30 or more degrees of freedom. That happens sometimes if we do Nordtest uncertainty evaluation, but usually you don't have that. Yeah? But the second one is there are at least 3 dominating uncertainty sources of comparable magnitude. And by comparable magnitude, what we mean is similar uncertainty indexes. And by comparable, we don't mean that they all have to be like 20%, 20%, 20%. If they are like 20%, 15%, and 30%, then that's comparable. Yeah? And we will see later on how we can use this rule. Yeah? And I will also teach you a more sophisticated thing, which is based on effective number of degrees of freedom and the so-called Welch-Satterthwaite approach. I think you may have even heard something about this, or maybe even done it, yeah, in the previous. Okay, yeah, we will revisit this. And now, can anybody say what might be the main reason for your output quantity distribution not really being normal distribution? What might be the main reason? I've already touched upon that, but it's good to spell it out here again. Yeah, Kamal, could you take microphone? In principle, yes, but you should say it in a more like comprehensive way. You see, in some cases, small number of replicates is not an issue at all, but in some cases it is. What does it depend on, whether it is or not? No. No. The answer is here. So yes, you are right. There's some input quantity obtained from a small number of replicate measurements. True, this is fine. But there's the second part to it, which you did not mention. This input quantity has high something, and that something is on this slide. Not necessarily. And by the contribution is quantified by what? Index. Yes. So, yes, the main reason why measurement result oftentimes does not obey normal distribution is that there's one important input quantity which has quite high uncertainty index, meaning high uncertainty contribution, but has been obtained as a mean of a small number of replicates. Next lecture, we will start calculation example where eventually we will discover exactly that. So we close here today. Yeah. I will leave this part, this well-shuttered right thing to the next time. And next time, please again bring your PCs, because the isogam with which we will start, we mostly do it by, or learn it by doing. Yeah, this is how they say it. Yeah, we take one example. Yeah, this is the second example, which already is the initial file is available for you on Moodle, and we start calculating. But for today, the lecture is over. Unless question, apparently not. So thank you, and we meet next Tuesday.